The sun puts out more energy in 1 second than 1 billion major cities would use in a year. We'll say, well, why would God make such a magnificently powerful object when we only need a small fraction of it? Well, he's God, why not?
If the Earth were to be orbiting an average star, it would be a red dwarf, and we wouldn't be here to be talking about it, probably.
Our star, I think, to be among the more stable types of stars, and he wanted it to provide steady amounts of energy for us, and so that's what it does.
We can see that we're just right where we need to be inside that habitable zone.
There's one shield after another, these ways that God has set up the earth for us. I think it all shows how this place was planned for us.
Every morning we wake up, there's a faithful companion that follows us through the day. Our lives would not exist without it. It's the sun, a hot glowing mass of incredible energy that impacts every part of our lives, whether we realize it or not. When you take a closer look into the sun, the facts are staggering.
The sun, of course, being the central star of our solar system and what's largely responsible for signs, seasons, days, and years, it's basically a large nuclear bomb, an incredibly efficient power source. The sun puts out more energy in 1 second than 1 billion major cities would use in a year.
The sun is like 860,000 miles in diameter. It's about 109 times the Earth's diameter. Sometimes show people sunspots. You see an image of the sun sitting here, and I see these little dinky spots. And I say, oh, those little tiny things? I said, yeah, but the sun is 109 times the diameter of the Earth, so those things are actually bigger than the Earth. Its mass is like 330,000 times the mass of the Earth, so it has 99% plus of the mass of the solar system inside of it, even though it only has about 1% of the angular momentum. The planets have all the angular momentum, which is kind of an odd thing when you think about it. It has a temperature of about 6,700 Kelvin, which in real temperature is around 11,000 degrees Fahrenheit.
And people say, well, why would God make such a magnificently powerful object when we only need a small fraction of it? Well, he's God, why not? It's not like it was harder for him to make that than it was to make anything else.
The internal temperature is on the order of millions of Kelvin. You can do a back of envelope calculation, just an estimate, and you get about 7 million for an average. I've done that estimate several times. Detailed models suggest the internal core temperature of the sun's around 15 or 16 million Kelvin, and that's high enough to sustain nuclear reactions, fusing hydrogen to helium. And we think that's the source of the sun's energy, and the sun can shine this way for 8 or 10 billion years, so not a real worry.
The core of the sun is where you have nuclear fusion taking place, and we have good evidence that that is taking place because it releases not only energy but also neutrinos. Neutrinos are these little ghostly particles that can go right through ordinary matter. They go straight from the core of the sun all the way to the Earth. There are several trillion of them going through you every second, amazingly. And they're hard to detect because they're so ghostly, but we do have neutrino detectors on Earth, and they've detected neutrinos coming from the core of the sun. So it's good evidence that nuclear fusion is taking place there. The next layer out is called the radiative zone because the radiation from the core streams out through that radiative zone. The next zone is the convective zone, or the convection zone, and that's where you have motion, all kinds of motion. The plasma bubbles up and carries energy from the inner sections of the sun out to the surface. And then, of course, you have the photosphere, the area that you actually see, and you get all kinds of interesting activity on that, sunspots and things like that. Sunspots are cooler regions where there's been a strong magnetic field that prevents motion. Magnets can prevent motion in plasma because plasma cannot move across a magnetic field line. And starved of their energy source, they just simply cool off. And so sunspots are chilly 4,000 degrees compared to the rest of the sun, which is about 6,000 degrees. Above the photosphere, you have a very thin layer called the chromosphere, and it's normally transparent and difficult to see, but you can see it during a solar eclipse. That little ring during a total solar eclipse of very colorful prominences and things like that, that's the chromosphere. Chromo meaning color, because it often appears vividly colorful. Beyond that, you have the solar corona, which is a much larger layer of very thin hydrogen gas that streams out into space. And it's really can't be seen by eye, but we do have spacecraft that can detect the solar corona.
So where did the sun come from, and how old is it if it came about by chance? We weren't there, of course, so how do we know? Does the secular story match up with the facts and physics, or does the evidence support a biblical worldview?
The sun is allegedly billions of years old, and it's probably a third generation star, they would say, meaning that the first stars that existed, which would be called population 3, they're made of pure hydrogen, helium, trace amounts of lithium, because those are the only elements that can be created in the Big Bang. Not surprisingly, from a creationist perspective, we find no population 3 stars anywhere in the universe. Then the second generation of stars, which would be called population 2, would have small amounts of these impurities, which are called metals. In astronomy, anything heavier than helium is a metal, interestingly. And then the sun has a fairly large amount of metals for a star, approaching 1%, something like that, as opposed to just a fraction thereof. And so they think it's a third generation star, which is called population 1. There are problems, of course, with the secular view of the age of the sun. One of them is called the faint young sun paradox. And this has to do with the nuclear physics that takes place in the core of the sun. Our understanding of nuclear physics suggests that as hydrogen is fused to helium, that reaction eventually becomes hotter because it changes the mean molecular density of the core, and that causes the sun to gradually heat up and brighten. And so, by secular thinking, the sun must have been about 30% fainter when it first formed, about the time life was supposedly first evolving on Earth. But if it was that much fainter, Earth should have been an iceberg. It was getting not nearly as much energy as we get today, and yet if anything, the geological evidence suggests the Earth was warmer in the past. And so that problem is called the faint young sun paradox. It's not a problem, however, in a creationist worldview, because in 6,000 years, the core temperature of the sun hasn't changed very much.
There's an aspect to the sun that I think is very interesting that you don't often hear about. The sun, according to the secular solar nebula model, supposedly formed from this big cloud of gas and dust that then collapsed into a disk shape, and the sun formed in the middle and the planets. And as evidence for the secular model, a secular astronomer will point to the fact that all the planets line up pretty closely within a disk shape. There's no actual disk, of course, but their orbits line up in a disk, and they call that the plane of the ecliptic. There's an issue with this that's not commonly talked about. If that model were true, then we would expect the rotation of the sun to match the plane of the ecliptic. But it doesn't match. It almost matches, but not quite. The sun is actually tilted over on its axis by about 7 degrees. Now 7 degrees doesn't sound like much, but you have to remember how big the solar system is. Neptune, the furthest planet, is about 2.8 billion miles away from the sun. If the secular model were true, we would expect the sun's equator to line up with the plane of the ecliptic. It doesn't. Because the sun is tilted, it's off. Extend that out to the edge of the solar system and you see there's a 343 million mile difference between where Neptune should be and where Neptune actually is. And it's not just Neptune, it's all the planets. I'm using Neptune because it's the furthest one out. So you have to ask a question. If the secular model were true, why doesn't this match? Why doesn't the sun's equator match the plane of the ecliptic? Did something tilt the sun over after the planets formed? And if so, what could possibly do such a thing? Nothing we know of, other than something big enough to destroy it probably. Or did something move all the planets at the same time systematically? Which doesn't make sense either. There's something built into the very structure of the solar system that the secular model has a really hard time explaining.
At the beginning of Genesis, the Bible describes the days of creation as real 24-hour days. The sun came along several days into creation, and there may be a good reason for that. Some tried to interpret long ages in between the days of creation, which presents some big challenges to what we know about science.
According to the scriptures, the sun is made on day 4, which is kind of interesting because we had day and night before that. God provided the temporary light source. He made light on the first day, and He divided the light from the darkness on the first 3 days, and then He replaced that temporary light source, whatever it was, with the sun on the 4th day. People have asked, why did God do that? Now, the Bible doesn't specifically tell us, but one reason might be to displace the sun, making it fourth so that the Hebrews would be less inclined to worship it as the source of life. It's not the ultimate source of life. God is the ultimate source of life. And He is what creates on day one. The sun is merely to serve in a particular role. It's a created thing. In fact, you notice it's not mentioned by name in Genesis. The sun is simply referred to as the greater light, and the moon the lesser light. And by not giving them proper names, it again makes them less inclined to be like a deity that would have a proper name. One really interesting thing is that plants which make use of sunlight were actually created before the sun. The Bible tells us that God made light first, and divided the light from the darkness and the separation of the waters, and plants are on day 3. They're already using whatever that temporary light source was. So it's not a problem to have plants before the sun, and they were only there for one day before the sun anyway. That is a problem for those Christians who compromise and want to make the secular time scale line up with the biblical time scale. They would say, well, the days were long ages, millions of years each. It's a problem because you still have the plants before the sun. In the secular view, the sun comes before the plants, so you can't have that. And they say, well, maybe the light just appeared on the 4th day. I've heard a particular person that argues that view. But the Hebrew wording is very clear. God made the lights on those days. There's a different Hebrew word for appear. The word to make is asah, and it's what's used of the sun. It's made on the 4th day. It's not a problem if you take the Bible as written, if you let it mean what it says. It's a huge problem, though, if you try to compromise with any other position.
We know by studying creation that the sun is essential for life on the earth. It's as though our Creator designed the perfect placement of the earth and the energy of the sun to work together. In fact, it's called the Goldilocks zone, and it challenges the laws of probability if our solar system came about by chance.
Okay, sun produces energy that's radiated here. It takes about 8 minutes to get here. It's a wide part of the spectrum. The bulk of it's coming in infrared, which is blocked out, but we have visible that comes through. And that radiation that makes it through does several things. Number one, it heats the earth. We get warmer temperatures in the day and cooler at night. And there's a nice regulation going on there that gets into planetary and atmospheric sciences.
And of course, plants make use of the light, and they're able to take that and use that energy to create things like sugars. And then animals and human beings are able to eat those sugars.
Animals eat the plants, or they eat the animals that eat the plants, or they eat the animals that eat the animals that eat the plants. We all go back to plants, which all goes back to solar. And so this is free energy coming in, more or less. And only a tiny fraction of the sun's energy is actually hitting the earth, and only a tiny fraction is actually harnessed. If you're too close to the sun, it's too hot, you don't have liquid water, and without liquid water, life is impossible. If you're too far away, you don't have liquid water, it's all frozen, life is impossible. So you can define a very narrow zone, the habitable zone of the Goldilocks zone, and the Earth is there, and we don't have to move the Earth around to ask what would happen. We've got 2 planets, one on either side. Venus, too close, it's very hot. It's got the hottest surface of any planet, hotter than Mercury, which is even closer to the sun, because of the greenhouse effect that it has. And then farther out you have Mars, which is a very thin, inhospitable place, very cold there. The warmest day on Mars is still worse than the coldest day on Earth, so it's a pretty rough place. And so we can see that we're just right where we need to be, inside that habitable zone.
The Bible tells us that on day 4, God made our sun just for us who live on the earth. Astronomers have searched the universe for more stars and estimate there are 10,000 billion of them. With these numbers in mind, some say our sun is pretty mundane, discounting God's special design. But it's not mundane at all when you take a closer look.
You often hear comments about how our sun is ordinary or average, or as Carl Sagan once said, humdrum. That's not at all true. Our sun is unique.
There are stars that are much bigger than the sun, much bigger, some of them hundreds of suns across in diameter. But there are a greater number of stars that are smaller than the sun. But the sun is kind of in the middle of those two. And it turns out that red dwarf stars, which may be half the size of the sun, they're just everywhere in the universe. Chances are, if you're a star, you're a red dwarf. That's just the way it is.
Now, red dwarfs, as you can gather by the name, they're red and they're very small. They emit about 5% of the energy of our sun. So in order to get enough energy to be warm enough for there to be life here, the Earth would have to orbit the star very closely. So closely, in fact, that there would be a tidal lock, where the same side of the planet would always face the star. That means that you have one side that's always hot and the other side that's always cold and dark. So you can't have anything growing on the dark side, obviously. And there's another real question about whether anything could grow on the lit side of such a planet too, because the star emits reddish light, not greenish light, which is primarily what powers photosynthesis. So whether or not plant life could even exist on this planet is a real question. Of course, without plant life, we couldn't live because it's the foundation of the food chain. And even if all that weren't a problem, orbiting a red dwarf closely will get you into trouble eventually, because red dwarfs are very unstable and they flare frequently. They're sometimes called flare stars. They erupt and they blast superheated surface material out into space.
A flare is actually sort of a hot spot, a bright spot on the sun where magnetic field lines have snapped and they've released an enormous amount of energy.
So any planet that orbits these things close up gets sterilized. So if the Earth were to be orbiting an average star, it would be a red dwarf and we wouldn't be here to be talking about it, probably.
Some astronomers have been looking for solar analogs, that is, stars similar to the sun. We can look at the temperature of the sun, the size of the sun, so what we call a main sequence G2 type star. And what they found very interesting about the sun is the fact that the solar analogs we find are very active. They have apparently a lot of sunspots, a lot of chromospheric activity, more so than the sun does. And these things vary in brightness, appreciably so. The sun doesn't appear. If it is, it's like, 0.001% or something. Well, some of these stars are varying by several percent. As you find more and more of these being very active, it's obvious that they're not the weirdos. The sun is the weirdo.
And even among class G stars, stars very much like our sun's unusual, most of those are in binary or multiple star systems. A binary pair is where two stars are orbiting their common center of mass. In a multiple star system, you can have 3, 4, 5, 6 stars orbiting their common center of mass. As you can probably guess, a system of stars like that makes things very complicated for any planet orbiting such a system. Sometimes it's going to be receiving a lot of energy and sometimes a lot less, depending on its relation to all these various stars. And its orbit may not even be circular, it might be more elliptical, in which case it's going to receive a lot of energy and then a little, a lot of energy, then a little. But we don't have that. We have a single class G star.
The sun is remarkably stable for a star, just remarkably stable, and that again is a feature that's designed for life.
Ever since the early 1600s, astronomers like Galileo observed sunspots. Then later, more powerful telescopes revealed solar flares. Over the years, scientists began to understand the power and effect of these features. But there's still so much we don't know. It seems sunspots and solar flares are part of a design system.
Many people think that these things, if you look at the sun through a special telescope, you can filter out a lot of the light. They'll think a solar flare will just jump out at you. It doesn't. A solar flare puts off minimal energy in the visible part of the spectrum. The real heavy lifting is in the ultraviolet and in other wavelengths. It's associated with sunspots. When you have a sunspot maximum, we have an 11-year cycle, roughly 11 years, where the sunspots are great in number and where they're less in number. And during solar maximum, you have a lot of magnetic activity on the sun. You get a lot of solar flares. You get outrushes of particles from solar flares that send these charged particles out towards the Earth. They cause aurorae, or northern lights. And you got the sunspot cycle that is tied to magnetic effects. We don't really know what causes the magnetic fields to kick up and stuff. We're just kind of starting with a gimme there on all of this. And the sunspot cycle does appear to have a long-term effect on climate. That's almost undeniable. The reason why people don't talk about it much is because there's no known mechanism connecting it. Again, suggesting there's a lot we don't know about the physics of this thing going on. But the sun is stable, but it also has these variances in sunspots.
The sun does have a periodicity to it. There's a sunspot cycle where you find that every 11 years you get a lot of sunspots with fewer in between. And we've now found that that's actually half of a much larger of a 22-year cycle, and that's linked in with solar magnetism. Sunspots are magnetic. They're related to magnetic field lines preventing convection underneath them, and so they cool off. But the sun has an incredibly interesting and complex magnetic field. It has several magnetic fields. It has a polar magnetic field, just like the Earth's, North Pole and South Pole, but it also has toroidal magnetic fields, for which there's no equivalent on Earth. A toroidal field is where it wraps around, like that. So if you were to hold your compass, it would point east-west, and you could go all the way around in a complete loop. And there's at least two of these, one in the northern hemisphere and one in the southern hemisphere that's reversed. And so it loops around sort of like that. It's rather interesting. And there's a complex interplay of these. There's also lots of little bits of magnetism all over the surface that just sort of have a random orientation. We've noticed, though, that the magnetic fields, that these toroidal magnetic fields, what we think are there, sunspots tend to occur at those latitudes. So you tend to find sunspots at specific latitudes on the sun and very few near the poles. And these zones actually move toward the equator with a period of about 11 years. And then the sunspots go away, and then they start up again, move toward the equator, and they start up again. And we think that's because the sun has what's called a meridional circulation, which I actually was able to detect in my doctoral dissertation, my doctoral research. And that pushes these magnetic field lines toward the equator, where they annihilate, and then new ones form. And this happens every 11 years. And the polar magnetic field reverses. So Earth's North Pole has been the North Pole for quite some time. The sun flips every 11 years, and it ties into that large 22-year cycle.
Overall, our sun is a very stable star. Yet sunspots and solar flares have the potential to cause us great harm. Through God's providence, He has designed our Earth with many protections against these harmful elements.
Some of the sun's magnetic field lines of force get all twisted and tangled up, and then they'll rip out some gas of the sun with them, and then the magnetic lines of force release some of their energy suddenly and spew out these particles violently, and sometimes they're headed toward Earth.
When a flare happens, if it's directed away from the Earth, we experience nothing. If it's directed directly at the Earth, then a lot of times that flare will release cosmic rays and things like that from the sun. And those will impact Earth satellites, and they can cause static on those satellites. If the flare triggers what's called a coronal mass ejection, which is where lots of material is released away from the sun, and if it's directed toward the Earth, you have two possibilities. One, it could do nothing. If the magnetic field of the coronal mass ejection is aligned with the Earth's, it'll harmlessly pass over Earth's poles. On the other hand, if it's opposite Earth's magnetic field, it will disturb Earth's magnetic field, which vibrates particles that are trapped in Earth's magnetic field and causes them to glow, and you get what we call the northern lights.
And the magnetic field acts pretty much like a shield. The particles will just spiral around the lines of force and come down near the magnetic poles, and they produce the aurora borealis and the aurora australis, the one in the South Pole. In hitting the Earth's magnetic field, they do create surges of magnetic field on the Earth's surface that can disrupt power networks. If you have a big, large set of power lines acting in which this magnetic field has changed, you'll get surges of high voltage, and those will sometimes do damage. At the same time, the Earth's ionosphere is excited by these particles, and the communication satellites get damaged, at least disrupted by these particles. So a lot of interesting things happen.
Aside from generating these beautiful northern lights, which is just delightful, it's actually a design feature, it's a life feature of the Earth that it has this magnetic field that deflects this harmful radiation harmlessly around us. It doesn't prevent all of it, but it prevents enough of it that life is possible, and the atmosphere contributes a bit as well. If we didn't have that magnetic field, it would be a problem. And in fact, the astronauts in space, as long as they're orbiting around the Earth, they're still inside Earth's magnetic field. But if they go to the moon or something like that, it could be an issue. If a major solar flare happens, it could cause problems for astronauts in space. And that's something that astronomers are looking into as they plan for things like a mission to Mars or something like that. Mars doesn't have that protective magnetic field, and so they'll have to find some way to deal with that problem. But the Earth is specially designed for life.
The sun is a huge energy machine, and it could be a danger to us. And as we look at the design of the Earth, the solar system, we have realized that there are several invisible shields that protect us and make life possible down here. For instance, the sun is a noisy place, continual nuclear explosions on a grand scale. If we could hear the sun, we'd be deafened. No, we'd be flattened. But of course, sound does not travel through the vacuum of space, and so we get the pleasant morning light, but not the sound. The sun gives off what's called the solar wind, which is a form of radiation, fragments of atoms, and radiation could be a hazard to us. It doesn't make it here. It gets caught up in the Earth's magnetic field and gets turned aside. The sun gives off what's called ultraviolet light, which can cause skin damage and problems. That gets absorbed by the ozone layer, which is high in our atmosphere and is still there and is still healthy and doing a good job of protecting us. The sun gives off X-rays, and they can be dangerous, but they never make it through the upper atmosphere. They're filtered out on the way. There's one shield after another, and I'm sure we haven't even found them all yet, these ways that God has set up the earth for us, and the other planets do not seem to have these shields. They have their own hazards and dangers. I think it all shows how this place was planned for us.
Even though we can't get very close to our sun to study it, much research has been done to try and understand how it keeps producing energy. It's a process called fusion. Fusion seems pretty simple at first, but extremely difficult to replicate here on Earth.
And when you talk about the sun getting its energy from fusion of hydrogen to helium, it's the same mechanism that powers a hydrogen bomb, which is the most powerful nuclear weapon we have. It's a fusion bomb, not a fission bomb like the atomic bomb was and is.
Now in the nuclear area, there's two processes. There's nuclear fission, and we do that with our nuclear reactors and naval ships. Nuclear fusion, we've never been able to have a lot of control of. We have some nuclear weapons, but that's not exactly controlled, and we're still working on that to try to harness that. But anyway, the sun does it, and all the stars, even though we can't do it. The sun is converting hydrogen into helium. This can happen in the core of the sun where you have multi-million degree temperatures and enough pressure, enough density to pull that off.
You know, when you burn a piece of wood, a piece of charcoal, that's a set of carbon atoms, and you're bringing some oxygen atoms, and oxygen and carbon like to stick together, whack, and so they release some heat too. So you're fusing atoms. In the case of nuclear fusion, you're fusing nuclei that like to come together, whap, and release some energy. So there's some similarity there. So, and it does happen, and we look at the particles that come out of the center of the sun called neutrinos that are liberated by fusion. So we have a pretty good idea of how much fusion is going on inside the sun.
The design of our sun is genius. From what it produces, there are just a few forces at work to produce our sun's immense energy supply. The laws of physics, established by our Creator, allow the sun to provide exactly what we need to survive.
You have what's called hydrostatic equilibrium. A big fancy word. All that means you have two forces. You have gravity pulling in on the sun like this, and you have pressure pushing out. And the two come to a balance. If the pressure is a little greater than the gravity, then the sun would expand. And as it expands, it would cool a little bit. That would lower the pressure, and it would reach a happy medium again. If gravity's stronger, it pulls in, and as it pulls in, the pressure will increase and it will halt again. So it's self-regulating.
The energy that is released from the core causes an outward pressure that is exactly balanced by the inward force of gravity. Those two things are just precisely balanced, and so the sun remains perfectly stable. As long as it has fuel, it will continue to do that.
So the sun sitting there under this balance, as the interior of the sun produces energy in the form of the heat from the reactions, it's transported outward and then radiated out into space. You got another equilibrium between, it's called thermal equilibrium, which is basically the energy radiated away is equal to the energy produced inside. And these balances are not magical, they're physical. And if they were out of balance, they would quickly readjust and come back into balance. It's a perfect nuclear reactor.
The sun is losing about 4 million tons of matter every second, day and night. And of course it never stops because the sun is always shining somewhere. And so you say, well, how long can that happen? Are we going to get a dark sun one of these days? And all we can say is that if you could see the gas gauge of the sun, it's still pinned on full. It doesn't even miss that 4 million tons per second. It could do that for billions of years. I think the Lord has other plans, but the sun has plenty of energy for this whole age that we live in.
When scientists look across the universe at the billions of stars in our galaxy, the uniqueness of our sun becomes apparent. Many stars are quite unstable, making it impossible for life to exist in those systems. Our sun appears to be designed to sustain life for many years to come.
Since the sun is powered by conversion of hydrogen into helium, and since the sun has a finite amount of hydrogen, eventually it would run out. And in the secular view, they'd say, well, then it swells up into a red giant. Regardless of whether or not they're right about the details, the fact is the sun has a finite amount of fuel.
Well, it would take billions of years to do that, yes.
So from a creation perspective, what will happen? Well, we're not going to have to worry about it because the Bible says there's going to be a new heavens and a new earth. But in the secular view, there's no hope.
Recently, they concluded a 30-year study of the surface of the sun, and they found that its output varied by less than 0.1% over the entire 30-year period. So we see other stars flaring, erupting, super flaring frequently. We see our sun amazingly stable.
People might ask, why is the sun so stable? What is the physical reason for that? And I don't think we really know the answer to that. The fact that it's a main sequence star certainly helps, but there are other main sequence stars that do have these super flares. Why is the sun usually stable? The fact is, we really just don't know.
God built our star, I think, to be among the more stable types of stars, and He wanted it to provide steady amounts of energy for us, and so that's what it does.
Genesis 1 tells us that God spoke the sun, moon, and stars into being. When we study the sun, it becomes apparent how the Creator's attributes are demonstrated. In His love, the sun was created to sustain creation, to give us warmth, to give us life.
Well, we sure do depend on the sun. When you think about its immense energy and its power production, I think it's a good reminder of God's power because He spoke the sun into existence and all the other stars as well. So it kind of shows that our God has infinite energy at His disposal and gave us some in the form of the sun.
When I see the sun, I see this enormous object. I mean, so much bigger than the Earth is. So much power and fury, if you will. But it's controlled. It's stable. The forces within it we see in other stars are enough to destroy anything around it. Yet our sun is quiet and stable. Less than 0.1% difference in its output over a 30-year period. Contrast that with even other solar-type stars, stars very much like our sun, that erupt in frequent superflares once per century. Now, God didn't need to create other stars being unstable like that, with ours being the only one that we know of that is so stable. I think He did that as a sign to us about how unique our sun and solar system are, how well designed it is for us to be here, and the care of a loving God to design such a place for us to live.
I think one of the reasons that God made it later is to prevent the Hebrews from worshiping it as a deity, because it does a lot of the things that you would expect of a deity. It provides light, it provides energy, it provides for life.
I think about the working hypothesis that made science and the science revolution possible 400 years ago was that maybe some of God's characteristics were imprinted upon His creation. Stability and care for us, think of what you might see reflected in the sun, its properties given to Him by the Creator.
The sun is central to life on Earth. The more we study it, the more it reveals the impossibility of it coming about by chance and random processes. It was designed by our loving Creator to give us life and stability. Every day you see the sunrise or sunset, praise the Creator for His mercy and love. It draws us to worship the Creator for His amazing design and say, the heavens truly declare the glory of God.